Do you still see my screen?
Yeah.
Yep. Perfect, thanks. So I would like to welcome everyone to today's Excellence Seminar. This Excellence Seminar series is presented by Battery 2030 Plus. For those of you who don't know, Battery 2030 Plus, it's considered an essential part of the European battery ecosystem to invent sustainable batteries of the future. If you would like to know more about us and the initiative, please go to the website. You can find it simply by searching in Google Battery 2030 Plus. In May, the annual conference for Battery 2030 Plus will be held in Grenoble on the 28th and 29th. There are definitely still places open, including for young scientists. We always love to have young scientists present at our events. And so if you're interested in coming and presenting a poster about your work at Battery 2030 Plus, please submit your abstracts. You can do so here by Meet at www.meetbattery2030plus.eu or over the QR code currently on the screen. So the Battery 2030 Plus initiative has been organizing this excellence seminar now for quite a while. Here you can see some of the people that have presented at the excellence seminar in the past. And today we want to present, or the topic of the excellence seminar is perspectives in battery recycling. And we're very lucky today to have three speakers who are going to give us different aspects about battery recycling, particularly in Europe. The first speaker will be Martina Petranikova. The second will be Emma Kendrick, and the third will be Andreas Flegler. So we will open with Martina, and she will be talking about advances in hydrometallurgical processing of lithium-ion battery waste. So, Martina, I hopefully can end sharing, and then the floor is yours.
Thank you very much. I will share my screen. Can you see it?
Yes, but not in presentation mode.
Yeah, I think it's coming. Let's see. Okay, what about now?
Perfect.
Yes, good. I hope you don't mind. I will switch off also the camera because it's a bit weird to see yourself and also to talk to the screen. So thank you very much for inviting me to have this presentation. And just to introduce myself, I'm from Chalmers University of Technology, which is in Gothenburg in Sweden. And our group has been working for over 15 or 16 years on the battery recycling. And today, okay, so some difficulty to move the... Okay, good. So today I will talk a little bit very shortly about the battery materials for those who are not that familiar with what we can find in lithium-ion batteries, and then also very shortly about the motivation behind the recycling, and then I will focus on the hydrometallurgical processing of the lithium-ion batteries, and then I will also share some research from Chalmers. And this is known for majority of us that in European Union, we are going to have a lot of battery producers and also car producing using electric or the batteries. But what is important for us as for the European Union is that we don't have the resources to actually make those batteries from. So that's why the recycling is so important, especially for us. And for those who are not that familiar with the battery composition, just to shortly that what we can find in lithium-ion batteries is mostly transition metals. So we either have lithium cobalt oxide, which is mostly in the small devices, and then we have nickel lithium or lithium nickel manganese cobalt oxide, and then also these days lithium iron phosphate, and then also the structure with aluminium. And what is maybe interesting to remember is that nowadays the effort is to decrease the content of cobalt for its price and also for its criticality. But we have to keep in mind that if we are decreasing the amount of this valuable element in the waste, then we are also decreasing the motivation for the recycling or incentives for the recycling for the companies. To just keep in mind that if we are decreasing some valuable element in the waste, then it's not that interesting to recycle. On the anode side, what we have is mostly graphite, and it's mostly artificial graphite, which is used in the batteries. And us as chemists who are using chemical recycling, we like graphite because graphite is a very neutral material for the hydrometallurgical processing. It's very easily recovered, and I will show you later where in which step. So it's a very good material. But what is also considered to be used, and what is also used are different doping elements, which can be like titanium or tin, which then it complicates hydrometallurgical processing. And for those who are developing the batteries, it's very important to remember that these kind of the elements, if they enter the recycling streams, then it's quite difficult to get them out from them. And then we also have electrolytes. It's mostly lithium salt and also some organic solvents. Usually I call these troublemakers in the recycling because it's always a problem to remove them, and they are also causing some problems in the hydrometallurgical processing if they stay within the waste. And then what we should also remember is that inside we have a binder, PVDF, and then some current collectors, which is metallic copper and metallic aluminum. So what is the motivation for the recycling these days? Of course, we are in European Union, so we have to obey the law. So the first and main reason is that we have a battery regulation, which requires us to achieve some efficiency in the battery recycling, and it is focused on the transition metals and then also on the recovery of lithium. So it sets some values which we have to be able to reach in 2027, and then in 2031 it's even higher, which is quite challenging for the recycling processes. And not only this, but except that we have to achieve some recycling efficiencies, then we also will have to, or battery producers, they will have to use some recycled material again in the production of the new batteries. So that is also quite challenging these days. Another reason why we should do the recycling is that we have the materials and metals which are present in the lithium-ion batteries. They are also on the list of critical raw materials for the European Union. And now recently it was even manganese which entered the list. And then also copper and nickel. They are not critical raw materials, but they are included as a strategic raw materials. So quite a lot of elements and elements are in the batteries are also on these lists. So there's another reason. Another reason is also, of course, profit for the recycling companies, because what they do is that they can sell the metals and materials recovered from these batteries, but then also in European Union, we have extended producer responsibility, which comes with the gate fees, which these days they are from 0.5 to 2 euros per kilogram of the battery. Some companies are even on the zero because the material is available. And then of course, metals, they are quite still valuable, even lithium hydroxide. The prices has been changing by time, but still, it's a very valuable material in those batteries. And then another reason is that we have to fulfill the demand. So we have a quote from the recycler who says that the recycling cannot provide enough supply, so we have to continue mining. And then from the miner or from the primer producer of nickel, we have that recycling is necessary because the primer sector or the primary production of the metals cannot satisfy the demand for nickel, for example. So then to be able to have enough materials for the battery production, we actually have to do the recycling. So how it is actually done these days. So for maybe many of you are familiar how this is done these days, but in general, we have two main roads. So one is pyrometallurgical road, where batteries are smelted together, very often together with nickel metal hydride batteries. And what is recovered is iron, nickel, cobalt, and copper. But it's important to remember that this is recovered in a form of alloy, which has to be then sent for the chemical processing to separate these metals from each other. Usually what is lost is manganese aluminum electrolyte. These days, there are also efforts to recover lithium from these recycling streams, but this is just in the beginning. The main road which we can see is the mechanical pretreatment, and then the black mass recovered from this mechanical pretreatment is sent to the chemical processing. Very often we can see, and now it's even like coming back, is the use of thermal treatment to handle the electrolytes and also better separation of the active material from the foils. And since I'm supposed to talk today about the hydrometallurgical processing, today I would focus on the main steps which are used in the chemical processing. And the first step which we start with is the leaching, where we usually recover all the metals, we get them in the solution. And then the next step, what is used is to remove the impurities. For us, the main impurities are iron, aluminum, and copper. If the mechanical pretreatment is effective, then usually these are at a very low concentration, but usually we still have to remove them before we are going to process transition metals. And very often what is used is either solvent extraction, the process I will talk about that later a little bit, or co-precipitation. And then lithium is usually recovered as the last one. There is also now an approach where transition metals are recovered before the impurities. So as it is written there are a lot of combinations and versions of hydromechanical or hydrochemical processing which can be used for the battery recycling, and also a different combination of them is being used, and you will see later. And since I always say that I'm a teacher, so not everybody is familiar also with these terms, if I'm talking about some chemical terms. So I will talk a little bit what the leaching is for those who are not familiar. And the leaching is that we have our black mass, which in this simple form, we can consider that we have some transition metal oxides, we have maybe some copper from the foil, and then we use the acid. We apply some time and also some temperature, we mix it for some time, and then what we get, we dissolve these metals into the solution, and we call it that we get them in the ionic form. And then we apply filtration or the separation. And then in this step, we very easily recover graphite, because graphite is not going to be dissolved in the leaching media, which is usually acid or some basic, or it can be inorganic or organic acid or diputetic solvent, also used these days. And this is the point where we can get very pure, or we can recover the majority of the graphite. Usually the efficiency of the leaching is very high when it comes to the metal, so we can get almost all the graphite in this solid form, and then we get all the metals in the solution. So usually this step is very effective these days. Another step which is used in the hydrometallurgical processing very often is the precipitation. And mostly the point is to sort of like get this metal from ionic form back to the solid form. So we can use different agents. It's very often sodium hydroxide is being used, but also, for example, for copper, it's very often some gas media. And again, we apply this media to the solution where we have our metals, the metal we want to remove precipitates, and then again, we use a simple filtration, and then we can recover or remove this metal. When it comes to the precipitation, the efficiency is usually also quite high, so we can remove from 98 to 99 of the impurities. What is maybe good to remember that very often in this step, we have some loss of the transition metals. So that depends on the technique or how the process was effective, but the loss can be from 5 to 10%. So then after the removal of the impurities, then we have our transition metals plus lithium still in the solution, but still if the process wasn't very effective or completely effective, then we still have some small impurities in the solution. Another method which has been used quite often for the separation of the transition metals is solvent extraction. Because transition metals are very similar to each other, it's not that easy to separate them just with the precipitation. So very often solvent extraction is used. It's a technique which is very old and being used in the primary production of metals. And the main principle is that we have organic molecules which are very selective. And very often we use the molecules which we can sort of like trick with changing the pH. So if we set a proper pH of the solution and mix this solution with the organic phase, then we can get into this organic phase just the metal we want to recover. So the principle is that we mix these organic molecules with our solution, and then the metal we want to extract or we want to get usually gets into the organic phase. And then they have since it is organic molecule, it has a different density from the aqueous. So they get separated based on the different density. And then we wash these organic molecules, which contain mostly only the metal which we wanted to recover, with some clean acid, usually it's acid, and then we get the metal in the clean form. What is very important, especially for people who are working with LCA, is to remember that these organic molecules are not consumable, so they can be used for many years within the process. So sometimes solvent extraction is seen as a very sort of like a chemical consuming process, but it's actually not, because these molecules, they can be used for, some companies are using them for 10 or 30 years. So it's they can be reused again and again. For the separation of these elements, usually we use different organic molecules. So for manganese, it's very often this commercial D2HPA, and for cobalt, it can be Sinex 272. And the purity is actually very high because it's a very effective method, and we can achieve battery-grade purity for these metals. And also the recovery is very high. And then usually lithium is just precipitated at the end, because if we remove all the transition metals, then in our solution, we keep only the lithium, which then is precipitated. And the battery grade or the purity is very high. What is maybe important also to remember is that if we are talking about solvent extraction, it's usually not just only one step, but there are several steps involved. So we have some extraction of the metal, then we can have some removal of the impurities from the organic molecules. And then at the end, we have this recovery, which we call stripping. So it's several steps for each metal. Because for some companies, this can be either too difficult or too expensive method to be used, then also what is applied these days is just co-precipitation of the transition metals. And then again, lithium stays in the solution and can be used, but the purity is slightly lower for the transition metals product. So how it looks like for the future is that it is expected that the main sort of like approach which is going to be used in the recycling is actually mechanical pretreatment and then hydrometallurgy. And it is sort of expected because if we look into the directive we are supposed to fulfill and achieve these efficiencies in the chemical recycling or in the recycling of the lithium-ion batteries, then usually the hydrometallurgy provides this ability to fulfill and also achieve the purities which we have to have for the battery production. In Nordics, it is several companies, and all Northvolt and Fortum, they are using hydrometallurgical processing. Stena is using mechanical pretreatment. And just since we are talking about, or I mentioned that there are different ways how to do the recycling and use different techniques in a different combination. This is, for example, the Fortum's approach, where they are also using chromatographic separation for the separation of their metals. So it's again another technique used for the recycling. So what we do at Chalmers. Since I'm supposed to talk about the hydrometallurgical processing, but I wanted to just mention shortly that we are also focusing on the removal of the electrolyte, and we are using supercritical CO2, where we can remove the electrolyte. A colleague of mine, Dr. Buchak Ebin, and his PhD students, they are using supercritical CO2, where they can very effectively remove the electrolyte and then also the binder, which then helps us in the hydrometallurgical processing to get more pure material for the hydrometallurgical processing. So if you're interested in their results, they have published several papers, and they also, or you can also contact them. And when it comes to the group which is working on the recycling of chemical recycling of the batteries, we have developed two roads. The gray one is this very traditional one, which is quite novel, where we use the leaching, then removal of the impurities, and then we go for the separation of the transition metals. But we also wanted to focus on something shorter and maybe more feasible for the recycling companies and more easier. So then the idea was to get the lithium first before all the other elements, then remove the impurities, and then keep together transition metals, and then go for the synthesis of NMC material from this mixture. So we can skip all the solvent extraction or all the separation of the transition metals. And with this one, we cooperate with the University from Uppsala, and they are helping us to make this NMC material. So the first idea was to get the lithium first, and the main reason was that if we remember the directive, it's quite high also and it's going to be increased on the recovery of lithium. And usually what you don't see and don't hear is that there is a loss of lithium throughout this traditional way of the recycling. So some lithium is lost in the precipitation of the impurities and then also in the solvent extraction. And then also this is related to quite a large generation of the waste. So then the idea was to recover this first before everything. And what we did was that we did a thermal pretreatment, because that's also what we have been working on for many years. And when we do the thermal pretreatment, the pyrolysis, then we can transform this lithium from lithium oxide and also from salts in the form of lithium carbonate. And lithium carbonate is leachable with the water. So my PhD student did that, but we sort of started, or we stopped, and the efficiencies, and usually our efficiencies were approximately from 60 to 70%. So there was some limit how much can be actually recovered with the current setup. But what is positive about this approach was that the main elements which were leached was just lithium and then a little bit of aluminum. And then we looked also at the product, what we could recover, and we recovered lithium carbonate. It was mainly this, and then a little bit of lithium fluoride, because of course we have some fluorides in the system. So then lithium will likely bound to the fluorine as well. And we are still working on this method, and we would like to achieve much higher efficiencies, but because we met this limit, and it was actually confirmed at several universities in working in Europe with this kind of approach, we all got to this sort of like a limit and these numbers. So then another way was to use organic acids. And my PhD student, she started to work with oxalic acid and did experimental design and tried to find the conditions where we could selectively recover lithium. And what she has achieved was that she was able to recover 100%, almost 100% of lithium. But also what was very interesting in this approach was that with this experimental design, she also recovered 100% of aluminum. So in one step, we could recover all the lithium and then also all the aluminum, which is the impurity in the system. So then we could skip one step for the removal of the impurity. And mostly what, as I said, it was mostly lithium and then also aluminum, and then the rest stayed in the solid residue. So it was also very simple to then separate the solution from the solid residue. Then, because lithium and aluminum are quite different elements, that helps the separation. So then she also tried evaporative crystallization, and with the conditions she has been tested, she very effectively also separated lithium from the aluminum. It is also still the research which we have been working on, and we will continue also using different approaches to get good separation of the lithium and aluminum. But still, like already with this step, we have reached and we have separated all the lithium from the system, while copper and transition metals stayed in the solid form. What we have been also working on is mechanical activation of the black mass, because as we all know, there is also binder or glue, which is used for the cathode materials on the aluminum foils. And this glue can also affect the separation and then the contact of the leaching media with the material. So we have tested mechanical activation with high energy milling, And what we could see when we were testing the base conditions, that for the lithium and for the cobalt, the increase of the leaching efficiency was from 5 to 10%, which is not much, and it cannot sort of compensate for the energy need for this kind of the milling. But for aluminium, it was also quite important, and then or a little bit increased, so that can be good and improve the removal of the impurities. And maybe this doesn't look now very significant, but in case of need for the even increased efficiencies in the recycling process, this could be also one of the steps where the recycling efficiencies could be improved for the material recovery. What we have been also working on a lot is, together with Nurion, who is the producer of hydrogen peroxide, is to look into the different consumption of hydrogen peroxide when it comes to the different NMC materials. And what we also looked into was actually the way of dosing the hydrogen peroxide. Hydrogen peroxide is used to leach all the cobalt and transition metals, because we need to change the oxidation state to get it into the solution. And the one positive of this chemical is that it doesn't come with any other impurities. So when it reacts, it decomposes to oxygen and to water. So it's a very clean chemical. But it's quite expensive chemical, and it's also its consumption should be optimized. So we did the research on the optimization and then also on to defining the consumption, and we could see that it's mostly, in the most of the cases, it didn't matter how we were dosing, if we were dosing in the beginning of all the volume needed for the reaction, or we were dosing throughout the experiment. So at the end, the consumption was very similar. The only difference was for NMC 811, when the consumption or the effect on the manganese was slightly better if we multiplied the dosing. What we also did the research on was this effect of thermal treatment then on the consumption of hydrogen peroxide. And we have received industrial samples from different companies doing the recycling with different way and different thermal pretreatment. And the yellow line, it represents the pyrolysis, which usually shows to be the best option as a thermal pretreatment. Red line is incineration. Green line is without any thermal pretreatment, and blue one is a mild thermal pretreatment. And what we have seen is that if we use, or if the companies use pyrolysis, then usually very small amount of hydrogen peroxide is actually needed for the reaction of to achieve the complete recovery. And then also it's very fast when it comes to the pyrolysis. If you look at the red lines, then you can see that even though we dosed a lot of hydrogen peroxide for the samples which were incinerated, it didn't help that much to cobalt and also to nickel. So incineration is really usually very bad option for the recycling of the batteries, because if you achieve some temperature, then you can form the phases which are not that leachable at this kind of the conditions. So it can be harmful for the recycling of the batteries. We have been also focusing a lot on the optimization of the solvent extraction, and we did a lot of research on the manganese, which these days or previously we can see that a lot of recycling is done by its precipitation because it doesn't have any value. But maybe that now we can see that there is actually an increased interest from the industry to also recover manganese with the solvent extraction, because again, it got into this list of critical raw materials. And it's also needed for the production of NMC materials. So with this method, we can achieve very high purity. So we have optimized the process and developed the process where we achieved very high purities for the manganese recovered from the batteries. We have been also working quite a bit on the recycling of LFP, because we have been using organic acid and also deputatic acids and inorganic acids. Unfortunately, this research hasn't been published yet, so I cannot share what kind of the organic acid we have been using and also what kind of the deputatic acid solvents or inorganic. But what is interesting here to see that with organic acid we used, we actually achieved very nice separation of the lithium and iron throughout the time. So that could be one way how the lithium could be selectively recovered from the system, and then also to achieve that the iron and phosphorus will stay in the solution. With the diputetic solvent, it's actually the separation or selectivity wasn't that well, but still we are working on this research. And then when it comes to inorganic acid, what is quite interesting to see is that there is different kinetics of these elements. So if the leaching process is very short, then we can get lithium, the majority of the lithium very quickly, while the iron and phosphorus stays still in the solid phase. We have been also working on the recycling of the graphite, and there is a lot of research where there is an attempt to do the regeneration of the graphite, but our approach is to do the graphene from this kind of the material because it's quite substantial material generated in this process. And we have been able to make the graphene out of this material, but still this process and project is it still continues. So thank you very much for your attention. And if you are interested in our work, you can find us on the LinkedIn.
So thank you very much, Martina. For the viewers, please put your questions down in the Q&A box below. We will come back to all of these questions at the very end when we have the panel discussion with our three speakers. And so next, I would like to introduce Emma Kendrick, and she will present sustainable routes to recovery and reuse of battery materials. So thanks, Emma. The floor is yours.
Thanks, Gwen. So I'm going to talk a little bit today about what we're looking at to recover some of those battery materials and then looking at directly reusing them into a battery. If we think about sustainability, we need to think about it holistically. So where the materials come from, as Martina has already explained, some of these are on a critical materials list. There's a security of the supply that we need to think about. Also, how much of those materials are actually recycled? But then how do we use them to make those materials? How are those materials transformed into electrodes, into the cell in life? And ultimately reclaiming those materials at end of life to kind of complete that circular economy picture of use. And the things that we're really interested in are trying to reduce the energy inputs and the environmental impact of all of these parts of the value chain for these lithium-ion battery systems and potentially other battery technologies as well. The bit that I'm going to talk about today is recovery of those materials. Martina's already spoken of how we can recover them and then use them as a secondary ore to remanufacture. But is there a route that we can short loop potentially? So this is the list of critical materials, and just to highlight the number of materials that are used in batteries on this list, there's a huge number of materials. You can notice also at the bottom, which is interesting, the nickel down here and copper, which are not actually in the critical quarter, but are called critical because they're strategic materials, so really important in terms of the technologies that they're used for. And then I've just highlighted a couple that aren't, sulfur and iron. All of these critical materials are assessed by a supply risk and an economic importance. And incorporated into that calculation is looking at where the materials come from, the governance of those countries that they come from, where they're refined, and also looking at the recycling input rate as well. So the point being, if we can recycle more, actually the criticality can be reduced. And so it's not a static number, it is a number that we can influence through recycling. I mean, there's other things that we can look at as well to reduce the use of these critical materials. So we could substitute. So for example, lithium, we can substitute for things like sodium. Recycling, as I said, is really important, but also reusing some of those recycled materials and repurposing them in potentially other technologies. We could do a quick assessment, and I just wanted to highlight some of the value against the criticality between different cathode materials from different types of technology. So I've got lithium cathodes here, and then sodium ion on the bottom. And as you can imagine, just because we're substituting lithium for sodium, actually the value of these materials reduce significantly, because lithium is quite a relatively high cost material. And also reducing the content of lithium improves the criticality in some cases, but not all cases, because we're still using nickel and manganese in some of these materials. And if we particularly look at the value of these materials, remembering that the cost associated with recycling we do need to consider, then what I've done here is plotted some of the lithium primary materials against some of the lithium secondary materials that we may be recovering. So we have spodumene here, which is a lithium ore, and in Europe we get that mainly from the spodumene rock is mainly from Australia. In Europe, most of our lithium actually comes from Chile, which is from lithium brines. But if we look at the lithium content in spodumene compared to the lithium content in some of our battery materials per kilogram or metric ton actually contain significantly more quantity or value compared to our primary materials. Petalite is a clay, which also is a primary material. And even some of our very low cost materials like lithium iron phosphate and our lithium manganese spinel, these still contain a good quantity of lithium in comparison to our spodumene rock. So it kind of makes sense that we should look at recovering lithium from our secondary ores as well as our primary ores. I mean, in addition, the value of our transition metals are significantly larger. So cobalt and nickel have a very high value. And so it is economically viable to recover some of these high value materials. If we move, however, to lithium iron phosphate, as you can see, we're competing with the primary ores, but moving to some of the sodium systems, actually the value can be quite low. And we do need to consider how we do this recycling to retain some value rather than it being just the metallic value from the composition of our cathodes in these materials. In essence, short looping that recycling. So rather than taking it from a recyclate, using it as a secondary raw primary or secondary ore, can we just take it from the recycled material straight to an active material called recycling, direct recycling. And if we look at some of the values of these materials, either as a recycled recyclate or a recovered or a actual material that's used in batteries, you can see there's a big difference. And this is because people are still looking at the value of the black mass or the recovered cathode materials as only the metallic value contained within that material. If we can retain some of that value being the actual active material, that would be beneficial for some of these low cost and low value materials, for example. So these are the typical recycling routes that are possible. We can take it through a pyrometallurgical process, recover the metals as an alloy, the lithium, aluminium, manganese in a light fraction or a slag, which we can recover from that. Or we can, as Martina has already spoken about, do some hydrometallurgical processes to recover the salts and then remanufacture the active material components from this. Or we can directly recover the active material components and try and reprocess them back into an electrode and back into a cell. And this is very much what we're trying to do in a lot of our work. So we have several routes to trying to reclaim these materials, and these are just some examples. So we've got the typical process is shredding, and this is actually a Gen 1 Nissan Leaf cell being put through our shredder in the safety chamber out the back of our university here. This tends to mix all our very highly engineered cell components together, which we then subsequently have to try and pull out again. Or we can do some disassembly. And the top shows one of our researchers in a lab under a fume hood, I might add, doing some disassembly very carefully of some cells to try and separate out the anodes and cathodes so that we get less impurities in our streams for then reprocessing. Whilst we're also looking at trying to automate this, and in the video below you saw some automation of trying to identify the cathode, the anode, and the separating material so that we can separate them out again to try and look at creating purer materials waste streams so we can reuse some of these materials with as little processing as possible. And so what we have done is look at the disassembly and the shredding process. First of all, we'll take the shredding process. We go through a drying step to recover the electrolyte, and then an electrostatic process from the shred, which then ionizes the feedstock. The separator sticks to a drum, and we can just brush off the separator as a non-conductive material, and then keep the conductive material separate. What we do with this, and this is kind of the example of the separator that we get from this process. There's a little bit of contamination. It's rather low in mass because separator is low in mass, but we can separate it at about 97% efficiency from this method. After electrostatic process, we take it through a magnetic electrode separation process. And here we use a rare earth magnet on a belt, and we can exploit the active material properties to separate out magnetic materials from the non-magnetic materials. And what we do here, because the cathode materials tend to be paramagnetic, we can actually use that. And as long as they're stuck to the current collector, we can separate out the aluminium coated parts and the copper coated parts with the of the electrodes. So here's just some examples of the aluminium coated, which have been separated because we've exploited in this case, the NMC properties. And here the graphite, which is non-paramagnetic, which is stuck to the current collector, can be separated out as a non-magnetic material. So we need to take it from these kind of large pieces of coating to then produce powder. And we have a couple of processes to do that. We can use ultrasound delamination and then filtration, and we can produce the powdered black mass, separating it now into a cathodic black mass and an anodic black mass. So mainly graphite in the anode and mainly the cathode material in the cathode, whether it's lithium-ion phosphate or NMC. We've got some examples of taking this using NMC materials, which is a Gen 2 Nissan Leaf, where we've disassembled a module, we've taken out the pouches, and then we've put this through a shredding process. We've also compared quality control rejects, which is straight from the manufacturing line, where the cells have been rejected from a quality control process, and also an end of life from the module. Interestingly, in this case, the quality control rejects were not filled, they were open, and they're a few years old, which meant that the delamination was rather difficult and everything had kind of stuck together. The aluminium had basically corroded within the cell, which meant the only way that we could recover that, rather than using an ultrasound method, was actually to dissolve out the aluminium, which is obviously not really wanted, because ideally what we do is recover the aluminium as metal so that we can recycle that directly again, rather than having to dissolve it out and then using enormous amounts of energy to remanufacture aluminium. But this just goes to show that we actually need to be careful how we handle our waste as well, even from our processing, because chemical reactions just continuously happen. And so we need to know state of health of the cell after use, but also after it's been shredded or disassembled or dismantled. So we know what processes we can use for recovering of these materials. In this case, we were able to recover quite nice pieces of the cathode, grind it up into a powder, and then analyze the quantity of elements in here. In this case, we actually had very pure samples with very little aluminium or copper impurities. And by a simple relithiation process, just using a lithium source such as lithium hydroxide or lithium carbonate, we could actually relithiate this 532 material from what was the QC rejected and the end of life. After delamination, we lost a bit of lithium. We could reinsert these into the materials. And actually, both of them showed some pretty decent specific capacities, reversibilities, and cycle life, as you can see from this. Still need some work on trying to improve the delamination process, however. One of the issues that we do have is the binder. This just shows you that we have PVDF in this binder, both QC reject and the end of life. And using the sodium hydroxide, we can remove some of that. Sodium hydroxide actually attacks the PVDF in a hydrothermal process. And then when we fire it, that PVDF is removed. It does cause some issues in terms of particle size as well, because all the particles are stuck together, obviously. They weaken through the hydrothermal process or the sodium hydroxide. And once fired, we get a pretty decent particle size distribution, which is relatively similar to what we would expect from a pristine material. But PVDF is a problem. We burn it off, it means we're producing HF, which also has been shown to delithiate some of these materials if there's a large quantity around. So ideally what we'd want is something not PVDF that would be removed much more easily. And we can see this as an example in a lithium iron phosphate cell. This is a CALB lithium iron phosphate. In this case, we've separated it and we just use a simple water method to delaminate the material. We can soak it in water, heat it to about 40 degrees and it delaminates relatively easily. And you can see the aluminium foil here being left behind rather than being dissolved by sodium hydroxide. And we can create a very high purity material stream for this. And this is the black mass that we obtain. It still has its binder, some of its binder in, as you can see, which is CMC and SBR. But what we can do is take that directly and relithiate it again using lithium hydroxide or lithium carbonate. And what you see here is the recovered lithium iron phosphate, which has about 10% iron phosphate, which we've measured from both Mossbauer and refinement on XRD. And then relithiating it, we can recover and remanufacture the lithium iron phosphate. We get some capacity back, but the quantity of carbon that we end up with in this system is actually quite high, and we need to kind of look to try and improve or reduce the level of residual carbon from this carbothermal process that we've used to remanufacture the lithium iron phosphate. But it's a good start, and it shows that water-based binders are an efficient way of removing some of the issues associated with PVDF binders that only dissolve in things like N-methylpyridine or NMP. In this process, we got 90%, 97% recovery of our lithium iron phosphate from the cell, which is quite a good achievement. But we're still trying to reduce some of the waste that we produce from these processes. And what we've developed as part of the SIMBA project, the sodium ion project, is to try and reduce the waste that's associated with these delamination processes. And we've developed what's called an ice stripping method. What you see here is someone spraying some water on an electrode. It's placed onto a cold plate or in this case, an ice cream maker, and the electrode sticks to the surface, and we can simply peel off the electrodes, leaving very little active material left behind on it, in a quite a pure aluminium foil. And in this process, we use very little water indeed. Initially, we'd pour water on, we'd lay on the electrode and we'd pull it off. Just by spraying the water on, we can reduce the time that it takes to freeze quite significantly to about 10 seconds, which means we can start to think about incorporating this in potentially a reel-to-reel or in-line process for delamination. And it's quite a simple method. What happens is the water goes into the electrode structure, the porous electrode structure. It freezes because the heat transfer is so quick in those thin electrodes. We can take the heat out, the electrode sticks to the surface very quickly, and then the adhesion to the surface of the cold plate is so much greater than that to the adhesion of the current collector that we can simply just peel it off. We can wet the water, wet the surface in about 5 seconds, depending upon what the electrode is, and then it freezes in about 4 seconds, as you can see from some of these measurements that we've done. So using this, we've tried to look at reclamation and reuse of some sodium-ion samples as well. This is some hard carbon. These are carbon electrodes that we've made with CMC SBR. We've recovered this and then tried to remove the binder by a pyrolysis method. We've heated it from between 200 up to 500 to decompose the binder compounds in there. And you can see that as pristine particle size is about 10 microns. And when you start to when the binder is still present, you have a much larger agglomeration of about 100 microns in this case, even after grinding. But we do get some much better particle size when we decompose the CMC and the SBR about 300 degrees C. It doesn't decompose the SBR fully, but it does kind of denature the CMC somewhat. And looking at this, we can start to think about reusing it. This is the hard carbon in a half cell. We've got some good cycle life of the pristine, which is in the blue, and the reclaimed, the 300 are cycling pretty well. In fact, the 300 is as good as our pristine. Whereas we go up in higher in temperature, we end up with a much higher surface area. We also get higher first cycle loss and also lower capacity when we cycle it. Sticking this into a full cell, we get from the directly recovered, we can actually disperse this back into an ink again and recoat it and it performs almost exactly the same as the pristine, if not slightly better, whereas the 300 heated, we get a high first cycle loss, so a lower overall capacity in a full cell, but it is cycling quite well. And then moving on to end of life using the same methods, we can still reclaim our electrode materials using the same ice stripping method. We heat it again to 300 degrees. And we've attempted to use it directly at end of life, and we get in a half cell similar results. It cycles okay, similar to what we would expect for this material. But when we put it into a full cell, our 300 degrees heated actually performs quite well. We get a higher first cycle loss, but we get a good capacity retention with this material. So again, showing that we can start to think about recycling and reusing both scrap and end-of-life materials directly from the reclamation processes using only a little bit of further treatments. We're continuing to look at this further, and this is a project called Revitalize, which is headed by MTNU. which we're looking at some of the separation and direct recycling of different lithium and sodium-ion materials. So just to summarize, improving the cycling rates will reduce the criticality by improving supply risk. We've shown that we can use electrostatic and magnetic separation with large pieces of current collectors to reduce impurity levels in our black mass that we reclaim for direct recycling. Some of our issues are still about the binder. We need to really think about what binder we're using, if we can use different binders, and are there some better ways of negating the binder in these black masses. We've also shown that ice stripping can be used for delamination. It has a lot less waste associated with it, and because it's so quick energy as well for delamination. And we can use this, both of these processes, to show that we can start to direct recycle things like NMC 532, LFP and hard carbon have been shown here as examples. I'd like to thank the group. These people listed here are the people that have done most of the work that I've spoken about today, and the funding sources. And thank you for your attention.
Thank you very much, Emma. So as I mentioned before, we will take the questions at the end. And so for our last presentation of the day, before we move into the questions and the panel discussion, I would like to introduce Andreas Flegler. And he will present Design for Circularity Strategies to Enable Direct Recycling. So, Andy, the floor is yours.
So thank you very much, Gwen. Can you hear me and can you see the slides?
Yes, to both.
Okay, perfect. So in my talk, I will focus on the design for recycling to enable the direct recycling approach. So we've learned in the last two talks a lot of the importance of battery recycling, and also very interesting approaches also for the direct recycling. And in this talk, I wanted to show you some results and also some concepts to enable it via design for circularity for future batteries. First of all, I want to introduce shortly my group. Here in Würzburg, 35 people work on different topics of battery research, mainly on the lithium-ion batteries, also on sodium-ion batteries and solid-state batteries. And 5 years ago, we started with the direct recycling approach. And now we look also for the design for circularity for future batteries. So we've heard a lot of the different recycling methods, so the pyrometallurgy, the hydrometallurgy, and the direct recycling approach. And when we look at the different waste streams we have here, there's the question for which recycling method or which recycling stream is best for the recycling method. And we tried here a small selection. So when you look at the small batteries in the 3C sector, so in mobile phones or laptops or something like that, there we have a lot of different chemistries. And here we have to use the pyrometallurgy because we have no knowledge about the cell chemistry. For the larger batteries in EV or in stationary batteries, we have the knowledge. And here we can go with the hydro processes. And at the moment for the production scrap, the direct recycling approach can be done. But we will get a high number of new batteries with or LFP batteries with a low material value. And for this, we have at the moment no profitable recycling processes. Now the battery regulation from the European Commission came and regulates the material recovery and also the recycled content in the new batteries and also the battery passport. And with this battery passport, we will get more knowledge regarding the cell chemistry, and we can shift the different waste streams to other recycling processes. But there we have also the problem for the non-valuable materials like the LFP materials or also the sodium-ion batteries. And here we have to look into the design of the batteries to design them in this way to recycle it more easily. And with this vision, we can shift also this waste streams to more efficient recycling processes like the hydro process or the direct recycling approach. And to sum it a little bit up, what are the challenges to implement the direct recycling approach is, so we have a lot of different cell types, different layouts. We don't know what is inside the cells. Then we have a lot of mixtures in the black mass and all some impurities through the shredding process and so on. Then the recovery of the electrolyte is a big issue, and we have it's very hard or complex to automatize the cell opening of such different layouts. And also a topic is how can we upgrade older cell chemistries like the NMC 111 to newer ones like the MNC 811. But the potentials of the direct recycling approach is very high, so we can get the active materials as its structure back. So we have the NMC or the LFP in this structure. We have very high recovery rates and green processes. So here we can use water-based processes, which we have heard at Emma's talk. And it's also profitable for the low valuable active materials like LFP and sodium ion, which are increasing numbers come on the market. And also we can recover the other battery components. So also the carbon blacks, the graphite, the electrolyte, the current collectors, and the casing in a high purity. And the R9 framework, which is shown here, is it provides some 10 strategies for design for circularity. And we see that in the end of the battery life, we end up at the recycling or recover strategy. So this is only to prevent waste. So here we only get energy or elements back. But when we want to increase the circularity, we have to look at the first stage in the design and manufacturing stage. So here the rethinking is one of the key to think how we can design the batteries in another way to come into strategies in the operational use. So perhaps the R5, the refurbishment, or the R6, the remanufacturing. Here we want to use the active materials in its function back. So we have to look at this design phase. And this can be also a unique selling point for the European battery industry to look in this kind of circularity. Now I want to show you some approaches, what we're doing at Fraunhofer ISC. So we look at different topics of around the circle. So we start with the design for circularity in the cell production. Then the cell sorting. Here we are focusing on integration of marker particles as an identifier with a battery passport. Then we look at a disassembly of state-of-the-art cells and also for future cells. Then we separate cathodes, anodes, separator, and the casing. And then we go to the coating detachment for anodes and cathodes. The binder deactivation, which is a very key topic in this recycling process. Then the separation of the active materials, so separate the active materials from the carbon black. Then the regeneration and upgrading, and then we close the loop and use the materials again. In this talk, I will focus on this process steps, and I start with the design for circularity in the cell production. Before I start, we have in this process, we can bring the waste stream into this process, the production scrap via the coating detachment and the end of life cells and the beginning. And what we get out in the cell disassembly step, we get out electrolyte, separator, and casing. In the coating detachment, the current collectors, aluminum and copper foils. then the binder in the deactivation, and in the separation of the active materials, we can get the carbon black back, and then the anode and cathode materials after the regeneration. So for the cell production, we're focusing on the aqueous processing for cathodes, and here we need a surface coating and the tailoring of binders and also the integration of functional additives. First, the aqueous cell production, here we see it as a design for circularity. We have a lot of advantages. So we eliminate the NMP and also the fluorinated PVDF binder, and we don't need a solvent recovery system in the production anymore. This have a lot of challenges with it. It brings with it, and we have a degradation of the cathode active materials with a high nickel content. So we have a leaching of lithium, so exchange with lithium and protons, and also the pH value increases, and we get an aluminum corrosion of the current collector. To prevent it, we looked at the content of water, so how many water affects the leaching process. So we start with a ratio of 1:1. That's like aqueous processing, like in the aqueous processing step. And we see that we have a lot of leaching, and when we increase the amount, we see that we get we reach a saturated phase. So at a water-based recycling process, we have a saturated region, and we see that we have a lot of coatings like carbonates are on the active materials, and this gives a poor performance in the electrochemical behavior. So to prevent this issue, we coat the active material with a phosphate-based coating. Here we use the method of a spray drying. And with this water-based process, we can use water as solvent and also a water-soluble binder like CMC. This we incorporated in the electrodes and processed NMC 811 cathodes via roll-to-roll process and built pouch cells with the capacity of 3 amp hours and measured them over 45 cycles, and we see that with the coating, with this phosphate coating, we can increase the discharge capacity of around 10%. And this water-based processes will be a very is a very high advantage in the recycling step later on. Then also the binders is a key topic in the recycling, in the direct recycling. So here we looked at the different CMC species. So here we looked at different degrees of substitutions of the carboxy groups. And we see that a higher degree of substitution is a better solubility in the polar solvent. So we have a better distribution in the electrode and get better electrochemical performances. And also this higher degree of substitution is very good at the recycling process when we put the electrodes into water without steering or something like that. So we get a detachment of this electrode with a higher degree of substitution. So this is, in our opinion, a huge research area to develop new binders which can be easily recycled and extracted out of the recycling step. Then here a concept of a new project, it's called the ADREC-BUD project. Here we integrate additives which can be triggered. So we integrate them in 3 different areas of a pouch cell, one in the sealing of the casing, then between the interface current collector and electrolyte, and then we integrate it also in the electrodes between active materials and additives like carbon black and binders. As trigger materials, we use inductive heatable particles combined with blowing agents, different surfactants and coatings. And later on in the recycling step, we activate these triggers via perhaps the magnetic field or temperature or pH changes, and then we can easily recycle these components. Results I cannot show today, but we will publish the results soon. The next step is the sorting. Here we use magnetic particles as identifier, and we work also on an automating battery sorting process. The magnetic particles the research of the magnetic particles are done at the FHU in Erlangen. They use iron oxide nanoparticles, bring them together as a modular system and create their different IDs. So the magnetic particles are like a barcode or a QR code. They have a unique signal, and we can detect them via a spectroscopy, the magnetic particle spectroscopy. And the big advantage of this magnetic particles is that we can integrate it in the bulk of the cell, and it's not visible, and we can also use it as a counterfeit protection. So in the first step, we integrate it in 3 different areas of the cell. So one in the ceiling, then we mix it in the cathode, in the electrolyte layer, and also bring it on the inside at the separator. And for all 3 cases, we can detect the particles and detect the signals. And in the next step, we integrate different marker particles for different cell chemistries. With these particles, we can integrate in these different steps in our in our cell manufacturing step. So we can integrate it in the coating of the electrodes, in the stacking, or in the packaging. And we can directly integrate them in our data space. So we have digitalized our cell production, and here we can integrate these marker particles, which have which are the identifier the identifier in the cell, which give an access to the battery passport. In the next step, we look at the cell disassembly. In the cell disassembly, we look at the one hand for the opening of pouch cells, so the contactless opening. Here we use an inductive method. We focus the inductive field on the ceiling and open it via melting the polymers. And here we have to focus that we have a spot and don't burn the electrolyte, the flammable electrolyte. With this approach, you can open contactless the pouch cells and separate cathode and anodes and separator from each other. We want to automatize the opening of prismatic cells. Here we work in a European project called Reuse since the beginning of this year. So at Fraunhofer ISC, we built up set up a robot which opened the cells and separate cathodes, anodes, separator, electrolyte, and casing. This we built in a glove box and use the prismatic cells from the cell manufacturers Morrow Batteries and 11Es. For the coating detachment, here we use different methods. One is together with a partner from Germany with ImpulseTech or ReElements. Here we use the electric hydraulic fragmentation. Then we have a reactor which is filled with water. We can put inside the cells or also production scrap or only aged cathodes or anodes. Then we have shock waves and open the cells. Then in the first step, we receive the cell casing, then the separator and the foils, and then we have the delamination of the different of the electrode coating, and can sieve different fractions. When we look at detail and the different fractions, we see at the lowest, the smallest fraction, we have a graphite-rich fraction. So the graphite was distributed very well in the water with these shock waves, and in the sieving step 250 microns to 1 millimeter, we see larger particles. This is the LFP-rich fraction. So with this method, we can separate, or we can concentrate cathode and anode black masses for further steps. And then we work also for different chemical and physical detachments. Here we use different solvents with different temperatures. And for the physical method, we also use some different approaches, which the results are not published yet. So I cannot go into detail, but we see it's a very strong dependence on the binder type, and we also work on the scaling of these technologies. Then the binder extraction, I don't want to go into detail, but I want to say also, like Emma said, that it's a key topic to extract or deactivate the binder, that we have single particles to go further with them with further processes. For the separation of the active materials, we use a centrifuge technology. It's a semi-continuous centrifuge, and we pump in the black mass. So in this case, it's a LFP black mass with a carbon black. The centrifuge cylinder rotates, and the particles with the higher density or higher particle size end up in the centrifuge, and the smaller one goes into the centrate. And when you adjust the process parameters, you can earn the active materials in the centrifuge, and the carbon black will go into the centrate. This is a semi-continuous process. So when the centrifuge is filled, we have to stop it and earn the particles. And to prevent this, we build up an automated process for this. So we use a robot which can bring the cylinder into the centrifuge, and then in a cleaning section which runs automatically. And so we can use this, or we can transfer this process from a semi-continuous to a quasi-continuous process. What we see with the centrifuge type, we cannot recover materials with a higher density or with a higher particle size. For this, we developed with our partner SEPA a new centrifuge type. It's a drum centrifuge, and with this we can separate graphite materials from black mass and also NMC materials. And you can see in the SEM images that we can earn here a graphite with a very high purity in a high amount. And we have a lot of aqueous processes. So we have a lot of process water. And when we want to check if which materials are inside this process water, and looking for methods how we can put out the valuable materials out of this process water, or to clean it, we have in a project called IDCyclab with the partner Pure Devices, we developed a setup where we can measure lithium, fluorine, and aluminium in black mass or in process water. And the big advantage is that the measuring time is around 1 to 5 minutes. It's via an NMR technology, and we get out the information what is the concentration of these elements in the water. And this we have successfully qualified with the ICP, and it's we get a very good compatibility with the ICP. And for the regeneration process, I don't want to go into detail. Here we have a lot of other activities. And with this, I want to conclude my talk. So for us, the conclusion is that we need some regulatory frameworks to look or to give standards for the design, that you get an acceptance from the industry to use this design standards. And we have only when we implement this design for circularity strategies, it's profitable for the low-cost chemistry like LFP and sodium-ion batteries. And yeah, the battery sector could be a role model for other industries to gradually from a linear to a circular economy. And with this, I want to thank for your attention, and also I want to thank my group and also the project partners and the funding from the European Commission and also from the BMBF. Thank you.
Thank you very much, Andy. So this is then the end of the formal part of our Battery 2030 Plus Excellence Seminar.